Welcome back to the deep dive. Today, we're going to be tackling a challenge you might not even realize exists.
Oh,
It's how to make sense of blurry pictures,
okay.
especially the kind plagued by something called, have you heard of this? Poisson noise.
Poisson noise, yeah.
Yeah, so think of like those grainy, low-light shots
Uh-huh.
where you can barely make out what's going on.
Yeah.
It's a huge problem in fields like medical imaging where like a doctor needs to see every detail in an MRI
Right.
or in astronomy where like faint light from distant galaxies just gets lost in the noise.
It's not just about pretty pictures either.
Right.
Image segmentation, which is basically dividing an image into meaningful parts,
Yeah.
is the foundation for all sorts of analysis.
Yeah.
Without it, you've just got a jumble of pixels.
Exactly. And that's where this research paper we're diving into comes in.
Okay.
They've developed a new technique that's particularly good at handling Poisson noise,
Interesting.
and it's getting some pretty impressive results.
What's fascinating here is that this type of noise is fundamentally different from the graininess we usually associate with noisy images.
Okay.
Poisson noise is all about the randomness of how many photons actually hit the camera sensor. So it's more common in those low-light conditions.
So imagine you're a researcher looking at cell images under a microscope.
Right.
Dim lighting means Poisson noise is going to be a real headache.
Exactly. Traditional methods often assume a different kind of noise called Gaussian noise,
Okay.
so they don't work as well in these situations.
Makes sense.
This new technique called AITV, for anisotropic and isotropic total variation,
Okay.
is specifically designed to smooth out Poisson noise while still keeping those important edges sharp.
AITV sounds pretty high-tech.
Yeah.
Is it as complicated as it sounds?
The concept is actually quite elegant.
Okay.
Think of it like this. Imagine trying to smooth out a wrinkled piece of fabric.
Right.
Traditional methods are like using a regular iron.
Yeah.
Just flatten everything, you lose some of the fine details. AITV is more like a special iron that smooths out those wrinkles while preserving the crisp folds and creases.
Okay, I'm starting to get the picture.
Good.
So AITV helps us see those blurry images more clearly by tackling the noise problem head-on.
Right.
But how does this smoothing magic actually work?
It cleverly uses two different ways of measuring the differences between pixels.
Okay.
Think of it like measuring the distance between 2 points.
Okay.
You can look at the direct route or the total distance traveled along a grid. By combining these two approaches, AITV offers more flexibility than traditional methods,
Okay.
allowing it to smooth out that noise while keeping the important edges sharp.
So it's a more nuanced way of tidying things up.
Yeah.
Making sure we don't lose those crucial details.
Right.
Now, the researchers didn't just stop at smoothing, did they?
They did not.
They actually used this AITV technique as part of a bigger framework for image segmentation.
That's right. They incorporated AITV into a framework called smoothing and thresholding, or SAY for short. It's a two-step process.
Right.
First, you create a smooth version of the image using AITV.
Okay.
Then you apply thresholds to divide that smooth image into distinct regions. Kind of like coloring in a picture after sketching the outlines.
Ah, so it's like a 1-2 punch.
Exactly.
Smooth it out and draw the boundaries.
Exactly. And they even extended this framework for color images with something called slant,
Slat, okay.
which adds an extra step of converting the image to a special color space called lab space.
Lap space. Now that one sounds really technical.
It is.
What's so special about it?
Think of it this way. Instead of just looking at the raw red, green, and blue values of each pixel,
Okay.
lab space represents colors more like how you perceive them.
Interesting.
This helps the algorithm see colors in a way that makes it easier to separate different objects in the image.
So it's like getting a second opinion from your own eyes,
Exactly.
which makes a lot of sense.
Yeah.
Okay, so we've got AITV for smoothing
Right.
and SAT-SLAT for segmenting. The researchers put these two pieces together and came up with
AITV Poisson SAT-SLAT.
catchy.
The name might not be catchy,
Yeah,
but it gets the point across.
it does.
They integrated AITV into this framework, specifically tailoring it for images with Poisson noise.
Now here's where things get really interesting.
Okay.
They also use something called a maximum a posteriori, or MAP estimation.
Right.
I know our listeners like to understand the why behind the tech.
Of course.
Can you break that down for us?
Imagine you're a detective trying to reconstruct a crime scene.
Okay.
You've got some clothes, fingerprints, footprints,
Okay.
but you need to fill in the gaps to figure out what happened.
Right.
MAP estimation's kind of like that.
Okay.
It uses statistical methods to find the most likely original image, given the noisy data we have.
So it's like a puzzle where the noisy pixels are the clues,
Yeah,
and the MAP estimation helps put together the most probable picture of what the image looked like before the noise messed things up.
precisely. And to solve this puzzle efficiently, they use a clever algorithm called ADMM, short for Alternating Direction Method of Multipliers.
ADMM.
It's a powerful technique for breaking down a complex problem into smaller, manageable steps that can be solved iteratively.
So it's like a divide and conquer strategy for the algorithm.
Exactly.
Okay.
And here's the kicker. The researchers mathematically proved that their model is guaranteed to find a best solution.
Wow.
Think of it like searching for the lowest point in a valley.
Okay.
This model ensures you'll reach the absolute bottom, not just get stuck in a local dip.
So they've got the theoretical foundation down pat.
Yes.
But what about real-world performance?
Sure.
How well does AITV Poisson SAT/SLAT actually work when you put it to the test?
Well, they tested it on 2 commonly used data sets,
Okay.
Dry for retinal images and BrainWeb for simulated brain scans.
Oh, right.
And the results were pretty impressive.
Okay, spill the beans. What kind of improvements are we talking about here?
For instance, on the Drive dataset, which contains images of blood vessels in the eye,
Okay.
the AITV approach was able to correctly segment, on average, 95% of the blood vessels,
Wow.
even the very thin ones, compared 85% for the next best method.
Yeah.
So that's a 10% increase in accuracy.
Wow, that's a big jump. So AITV is seeing things other methods are missing. What about the
What?
brain scans?
In the BrainWeb dataset, they found that AITV Poisson SATkis was particularly good at distinguishing between different brain tissues,
Okay.
like gray matter and white matter,
Mm-hmm.
even when the images were significantly blurred and noisy.
Mm.
This kind of accuracy could be really valuable for diagnosing brain conditions and understanding how the brain works.
So it sounds like AITV Poisson SAT/SLAT is a real breakthrough in image segmentation.
I think so.
But like any complex tool, I imagine there are some knobs and dials that need to be adjusted for optimal performance.
Right.
What are those key parameters that researchers need to fine-tune? You're right, there are 3 main parameters they have to adjust. One that controls how closely the smoothed image matches the original noisy one.
Right.
Another that determines the level of smoothing applied.
Mhm.
And lastly, one that dictates how strongly the algorithm focuses on preserving edges. It's like a chef tweaking a recipe to get the perfect flavor balance.
That's a great analogy.
Mhm.
And speaking of balance, the researchers found that the edge preservation parameter is particularly important.
Okay.
They discovered that a middle ground setting,
Uh-huh.
not too strong, not too weak,
Yeah.
generally produced the best results across various images and noise levels.
Ah, the Goldilocks zone strikes again. It seems like there's always a sweet spot to be found.
Right.
Now, before we get lost in the technical details,
you're
I
right,
think
yeah.
it would be really helpful for our listeners to understand the broader impact of this research.
Okay.
Where could this technology really make a difference in the real world?
Well, the potential applications are vast. Medical imaging, as we mentioned earlier, is a prime example. Imagine being able to improve the accuracy of diagnoses from MRI, CT, and X-ray images,
Right.
especially when dealing with subtle abnormalities that might be obscured by noise or blur.
That makes a lot of sense. Early detection is so crucial for so many medical conditions.
Right.
So anything that can enhance the clarity of those images could be a game changer.
Exactly. It could even pave the way for more personalized medicine,
Wow.
allowing doctors to tailor treatments based on a more precise understanding of each patient's unique anatomy.
Now, I know we touched on astronomy earlier, but I'm curious to hear more about how this technology could be applied to those incredible images of distant galaxies and celestial objects.
Sure. Well, think about it. Astronomers are constantly pushing the limits of what we can see,
Yeah.
capturing images from the far reaches of the universe.
Uh-huh.
But these images are often affected by low light conditions and atmospheric distortion, leading to significant Poisson noise.
It's like trying to photograph a firefly in the middle of the night.
Exactly.
Not an easy feat.
By applying AITV Poisson SAT/SLAT to these astronomical images,
Okay.
we could potentially uncover hidden details and structures
Yeah.
that were previously lost in the noise. It would be like giving astronomers a new set of eyes,
Wow.
capable of peering through the cosmic fog.
That's an incredible thought. Being able to see those distant galaxies with even greater clarity could lead to all sorts of new discoveries
Yeah,
and a deeper understanding of the universe.
definitely.
But beyond medicine and astronomy, I bet there are tons of other fields where this technology could be useful.
You're absolutely right. Any field that relies on image analysis, could benefit from this?
Like what?
Think about robotics and self-driving cars, where accurate object recognition is crucial for navigation and decision-making.
Right.
Or consider material science,
Uh-huh.
where researchers need to analyze microscopic images to understand the properties of different materials.
And let's not forget about security and surveillance,
Oh, yeah.
where being able to identify faces or objects in blurry footage could be critical for investigations.
Very true.
The potential applications really do seem limitless.
It's truly amazing to see how cutting-edge research in image processing can have such a ripple effect across so many diverse fields.
Yeah.
It makes you wonder what other groundbreaking applications we might discover in the years to come.
That's the beauty of science. It's a never-ending journey of exploration and discovery.
For sure.
Now, I know our listeners are probably wondering if this technology is a silver bullet
Mm-hmm.
or if there are still challenges to overcome.
Of course.
What are some of the limitations we need to be aware of?
Well, like any new technology, there are always limitations and areas for improvement.
Yeah.
One of the biggest challenges right now is the computational cost of running these complex algorithms.
Okay.
Even with techniques like ADMM, which helps to streamline the process,
Right.
it can still take a lot of processing power and time to analyze high-resolution images,
Uh-huh.
especially for real-time applications.
So it's a bit like having a powerful engine.
Yeah.
It can do amazing things, but it also guzzles gas.
A fitting analogy.
Okay.
Another challenge is fine-tuning those parameters we talked about earlier.
Right.
Finding the optimal settings for each specific image and application can be tricky and often involves some trial and error.
Mm-hmm.
There's no magic formula that works perfectly every time.
It's a delicate balancing act for sure,
Yeah.
but I imagine as computing power continues to advance, these limitations will become less and less of an issue.
Absolutely. As processors become faster and more affordable,
Yeah.
it will open up new possibilities for running these sophisticated algorithms more efficiently and on a wider range of devices.
Okay.
It's like having a supercomputer in your pocket.
That's an exciting thought. And the research in this field is showing no signs of slowing down.
Nope.
Scientists are already exploring ways to combine AITV, Poisson, Satslet with other cutting-edge technologies like machine learning and artificial intelligence
Right.
to further enhance its capabilities.
That's right. The goal is to make it even more robust, adaptable, and ultimately more accessible to a wider range of users and applications.
It sounds like it's a really exciting time to be working in image processing.
It is.
This has been a fascinating deep dive into AITV, Poisson, Satslet.
Yeah.
But before we wrap things up, I have one final question for you.
I'm all ears. What's on your mind?
I'm curious about the bigger picture here. We've been talking about images, but could these techniques be applied to other types of data too? Could this go beyond just seeing things more clearly?
What's fascinating is that the principles we've discussed today using AITV and these statistical frameworks aren't limited to just images. They can be applied to any data with similar characteristics.
Okay, now you've got me really intrigued. Give us an example.
Think about financial data. It's full of noise and fluctuations, making it hard to spot those meaningful trends. Or consider climate modeling, where we're always dealing with incomplete data and trying to predict complex patterns. Could an AITV-like approach help us filter out the noise and uncover those hidden signals? It's a tantalizing possibility.
That's a really mind-blowing thought. So this isn't just about sharper pictures, it's about understanding the world around us more deeply. Using these powerful mathematical tools to cut through the clutter and find the real insights.
Exactly. And that, I believe, is the true power of the research we've explored today. It's not just a technical advancement, but a shift in perspective that opens up a whole new world of possibilities.
Well said. It's been an incredible journey, and I know our listeners will come away with a newfound appreciation for the magic of image segmentation and the incredible research happening in this field. It's amazing how these mathematical tools can reveal hidden details and help us make sense of complex information, whether we're talking about images or something else entirely.
It's a testament to the power of human ingenuity and our relentless pursuit of knowledge. Who knows what other breakthroughs await us on the horizon?
So to our listeners, the next time you're struggling to make out details in a blurry picture, remember the power of these algorithms working behind the scenes to bring clarity to the chaos. And beyond images, remember that these same principles might be at work in other areas, helping us make sense of the complex world around us. Until next time, keep those questions coming, and we'll keep diving deep for you.
As always, thanks for joining us on The Deep Dive.